efficient way to very efficient way to build an eGraph, but then backtrack to a previous version as efficiently as possible. We wanted the thing to be very high performance, so we use lots of arena allocation, and then we use integers as pointers into these arenas, but then you're on your own because you can't rely on Rust to tell you you're doing the right things with pointers. So we started using Verus to verify parts of the mechanics of the eGraph. And then we wanted to solve AC explosion. So as you know, when you use eglog, you often have to express associativity and commutativity using rewrite rules, and here we use canonization to implement the same as replacement for rules. And we also wanted batch-proof extraction for all equivalent nodes, and we came up with a shadow data structure like union find and very efficient least common ancestor algorithm. And so the semi-persistent and AC matching, like canonized AC matching, already exists in a SMT solver called AltErgo since 2008. So nothing I'm presenting here is new. The only new thing is like it's written in Rust and verified using Verus. Yeah, and also we just recently open sourced the code, so everyone's welcome now to use it or contribute. So semi-persistence, I'm going to start with that. That's the foundational layer. Functional data structures, you have fully persistent vectors or arrays where every time you modify the array, you keep track of a negative diff with respect to the previous version. And you end up with this forest of diff, and then you can restore any previous version, and you can also jump back to any later version as you want. The semi-persistence actually drops half of that capacity. You can just backtrack to a previous version, but what you gain is optimum read and write access to the current version of the most recent version of the array. And to do this, you just keep the current live version of the array at the bottom here, so with different values at different indices. And every time you do a modification, you basically store a negative diff of what that value was when you did the modification, and you manage these different versions as a stack. So you have this mark and restore protocol where every time you mark a version of the current version of the array, you're going to capture the first modification you do post-mark, and then you're going to ignore later modifications, and then at any point in time you can reverse to one of the previous versions, and you pop all the diff stack. So you get at most one diff entry per layer of the stack, so you have a guarantee of how big the diff could grow. You're never going to have a diff that grows too big. And you can always restore a previous version in a backtracking fashion. So this is an example of the lifetime of such a vector. So you can start the branch 0, you can start with the current version 0, 0. Then you can take a first mark of that branch, a second mark, a third mark, and then you can decide you want to backtrack to mark 1, and then you open a new branch in the history of the data structure. You can continue and then backtrack to an earlier version on the 0 branch, and start branching again. So which means semi-persistence supports backtracking, but very efficiently. And we have this discipline of like checking branch counter and depth along the branch to prevent you from trying to restore to an invalidated snapshot. So we have guarantees about not ever crashing, basically, and always being able to restore. So from this single primitive, we were able to build hash maps using open addressing, sparse sets, arena allocated linked lists, circular lists, and all the way up to a fully fleshed out union find, node caches, symbol registry, so everything you need to build an eGraph. And now with this semi-persistent discipline, we have an eGraph data structure that you can tag different versions along a branch. It starts recording diffs, and at any point in time, you can backtrack to your previous version by catapulting the negative diffs back into the eGraph, and you restore the current state, the previous state. And you have a capped size and very efficient diff encoding. And So this lets us now use EGRAPHS inside of backtracking algorithms very easily, and the memory consumption is kept under tight control. And to make sure everything works as we expect, we started proving all these foundational layers using Verus. So for each of the data structures, we have a math abstraction and well-formedness predicates that were proved with Verus. And the key properties of that backtracking mechanism is that when you activate diff tracking, the whole data structure basically behaves as a stack of deep copies, but it only stores sparse diffs. And since we have Verus also verification, we were able to very aggressively optimize the encodings without having any fear for bugs. But so that's how we achieved backtracking. So the second feature of that eGraph is that we offer native support for associativity and commutativity, and also idempotence properties. So we spent a lot of time making sure the surface syntax for that feature was ergonomic. So what you can do now is declare algebraic properties for your functions. AC are going to be represented as canonized multisets. ACI are going to be sets, and associative are going to be sequences. And you also have binary commutative operations where the canonization is just ordering of the operands. But so you realize, like syntactically, when you start working with this, you need to introduce in the syntax rest variables. So you can say I want to rewrite an or applied to a not of a not x, but then there's going to be a trail of like other elements in that multiset under the or. And then you need to be able to reference those variables in the right-hand sides of rules as well. So these variables are typed either multiset or set or sequence. So which means to make it ergonomic to express rules, you have to have that syntax that has basically rest variables and comprehensions. So the comprehension syntax on the right-hand side kind of looks like Python. You can say I want to match mul of A over add of X with multiplicity K, because that's a multiset term. And I'm going to have some rest multiset. And you want to map a constructor over that multiset on the right-hand side. So we have this comprehension syntax that lets you build new terms, and the double dot is the splicing, which lets you inline the transform rest variable into like a new term. So we have set comprehension syntax for ACI operations. We have multiset for AC operators, and we have sequence comprehensions for A operators. And every time we build a new term like this, it has to be recanonized on the fly. So flattened, canonized, sorted, everything happens implicitly every time you build terms. So yeah, so this also means that from an implementation perspective, we have really different kinds of nodes, unlike eglog or other eGraphs where everything's homogeneous in terms of representation. We have actually different types and different representations and different invariants for every type of algebraic property. So yeah, as I said, sorted pairs for C, flattened sequences with order preserved for A, sorted multisets and sets, dedupt, unique. And canonization also involves like representing everything using class representative at that point in time. So this interacts also with performance. So we use like arena allocations everywhere, arena allocators, which means our node caches are partitioned, and in each cache of nodes of any given type, we have like a dense indexing of the nodes. Like they all have like a dense identifier in 0n. But then we also have this global namespace where all the nodes live, so we handle that union ourselves. So we have a routing table that assigns global identifiers to nodes, but that routing table tells us global node I is actually local node J in some node cache that has that special representation. And we have this double, like this two-step ID allocation. But what we get is like a super cache-friendly way of representing nodes. of different types, but we don't have this homogeneous tabular representation that EGLOG has. So now I'm going to zoom into like how we represent variadic nodes. Nodes that can have like different numbers of children nodes, like the AC and ACI nodes in A. So what we do for these nodes is an AC node that represents a multiset, essentially. We're going to have a header node that has a fixed structure, like an operation and a start and stop index within a contiguous pool. So all the children of all the AC nodes are concatenated into a single node pool. And then a given node is just a slice of that pool. And so this means that we have a super cache-friendly layout, and we have a homogeneous representation for all these AC nodes, even though they have variadic, children lists. But this also means that when you recanonize nodes in place, and you discover new equalities between children nodes, those slices can shrink. So you could be tempted to like shuffle the things and keep everything compact. We just shrink the slice in place, and we just lose a little bit of storage. But we can basically maintain that representation. And that's homogeneous, and that's where we can do AC matching later. Like we can AC match on that stuff. All right, so now matching. So now we have these different sets of nodes with different representation invariants. And we want to have a homogeneous way of doing like pattern matching on them, and including AC canonized matching. So to do this, we used the Leapfrog approach that EGLOG introduced. And we basically, every round of saturation, we build 4 indexes of nodes. So one of them is the by-up index. So given an operator, give me all the nodes that have this operator as operator. And this is going to be a sorted index, so we can do Leapfrog. So these are just lists of integers, basically. We have the by repr, which given an E-class, give me all the nodes that are in that E-class. And the by child in position, so given an E-class and a position, like operand position, give me all the nodes that have this E-class in position as parents. So parents at the shy slot, basically. So these are for the traditional nodes with fixed arity. And for nodes that are variadic, we just index them via one of the child they can contain. So we have this index that goes from an E-class identifier to all the variadic nodes parents that have that child somewhere in their child list. So we can index into AC and ACI nodes like this using a single index. So now when you want to match a pattern like f of g of x and h of x, that's the case without AC nodes, just as a baseline. So the first thing we do is we decompose that pattern into atomic patterns. We introduce intermediate e-node variables. So u is going to be g of x, v is going to be h of x, root is going to be f of u, v. And basically that set of atomic patterns gets compiled into that procedure where you're going to iterate over the index. So for u in all nodes that have g as operand, as operator, let x be the child of u at position 0. And then you have a leapfrog stage where you're going to be like for every v in the intersection of the nodes that have h as operator and have x at position 0. And then for all the root nodes in the intersection of these indices, so operators that start with f, have u at position 0 and have v at position 1. So that's a 3-way leapfrog. Then you can emit a full binding. So every shared variables between those atomic patterns becomes a join key. That's the standard EGLOGS thing. So in practice, it's not a loop like that. It's every pattern gets compiled into like a sequence of instructions that gets executed by a VM. But when you want to introduce AC decomposition in that picture, all it takes is add a new type of loop that enumerates multiset matches, basically. So now if we have f of a applied to add of like x k1, y k2 as a AC pattern and some rest variable, we decompose into atomic patterns as well. So n1 is going to be an AC node with X and Y children, and then some rest that we treat as a multiset variable. And the root pattern is going to be F and A and 1. So we start kind of the same. We start from the root, let's say. We match all these nodes. We bind A, we bind N1. So in that case, N1 is going to be forced to be a node that has the AC operation add. And then at this point, that's where we start stepping into the AC decomposition of the pattern. So we bind the residual to all the children of node N1. So that's a multiset. And then for every X in the residual, we're going to enumerate bindings of X and Y. So we start by binding X. We bind also the multiplicity of X to K1. And then we subtract X K1 from the residual. And then we do the same for Y in the residual that's been shrunk. We bind Y, we bind K2, and then we do multi-step subtraction again. The residual now is going to be a rest variable, and we can emit a full binding that way. Then we add Y back into the residual, add X back, like continue looping. So what this does basically is it enumerates all partitions of the multiset, where you extract like X, one X and one Y, full cardinality, and just drop the rest of the multiset in the comprehension. So it's really like a very minor extension to Leapfrog AC matching. And since our index like in two AC nodes is like just a single homogeneous index, it's actually pretty easy to do. So in practice, we don't really compile those patterns into eager loops. We compile them into like sequences of instructions for a virtual machine that's embedded in the runtime. And the mechanics of it is basically we have a stateful iterator that implements those nested loops. And we can pull matches one by one from the iterator lazily. So this also avoids like blowing up the memory by saturating the memory. Like if you're looking for a specific match, you can pull them one by one and filter on the fly. You're not going to allocate storage for all these intermediate matches. But anyway, so since we implement maximum partition semantics for the AC matches, we're insensitive to the actual multiplicity of the elements in the multiset, and we won't blow up. So we're not going to literally enumerate all the possible multisets, but just maximum partitions of the multiset. We can also add multiplicity constraints in the language. So you can say I want to match X, but only if multiplicity is superior or equal to some constant. And then when you have multiple uses of the same variable with different constraints, we integrate all these constraints into an interval, and we basically filter on the fly like the matches that don't satisfy that constraint. Yeah, so now proof logging. So the way we do proof logging is to introduce a second ghost union find that we never compress. We don't do path compression on this one, so it keeps the full trail. And every time there's a merge, we record the justification in that union find. And every time a node gets recanonized, we also store it in a side array of nodes so that we can start again from the actual root thing and have the full history. And so we are able to explain any pair of like A, B terms that land in the same equivalence class by just doing least common ancestor search in that proof forest. And we discovered a very efficient LCA algorithm. It's called the Bender-Farag-Colton algorithm from 2000. If you want to do batch extraction, you have a linear path that pre-computes basically all possible least common ancestors, and then for any pair of terms, you have O1 extraction. So if you want to do batch proof logging, you can actually do that very efficiently. And all of that is also semi-persistent, so you can log proofs on the fly. All right. So in conclusion, there's not much there's not much novelty in that data implementation. All the IDs are pre-existing, but we try to implement them in a verified way. So we haven't yet verified the thing fully. So far, we've verified the lowest layers, the raw data structures, but we're working our way up to the actual eGraph invariants. And the next steps would be like I've seen a lot of very crazy extensions of eGraphs that I want to be able to use, but slotted eGraphs or thinnings or colored eGraphs and everything. All super interesting, but making sure you implement that right seems kind of tricky. So the goal with this was to put some formal verification scaffolding around an eGraph, trying to engineer it as well as possible, and basically have a place where people could come and experiment with new eGraphs algorithms, but also have that verification scaffolding around it. So that's why also we open sourced it to try to make this happen. So yeah, we hope that's going to be maybe a framework that people are going to consider when they want to implement tricky extensions of eGraphs. And yeah, that's going to be it for me. If you have any questions.
Thank you, Remi, for a great talk. We have time for a couple questions. One thing that I do want to emphasize is that you should go to that link. There's a lot of great code there and a lot of great also high-level documentation about the motivations and design decisions here.
Super fantastic. I was wondering if you could characterize differences on performance differences across workloads.
So I've compared the implementation to egglog, and in raw throughput and pattern matching, we have a 30% gain in terms of number of matches per second. But I need to confirm all of that because proving some parts of it have basically called for de-optimization. Mm-hmm. And now I'm trying to re-optimize everything. So we haven't yet conducted extensive benchmarking. But cool. Yeah.
Very exciting. Thanks so much.
Thanks for the talk. Does it get tricky if you have a lot of constraints on what is in the set? I can imagine if your multi-sets or sets get quite large, enumerating all the partitions will get very expensive. But in practice, and that might be the user's fault for posing such a problem, but it's also possible to pose problems where that wouldn't be an issue. It seems like it's hard to constrain the enumeration effectively. Yeah,
so we're already happy to contain the full explosion, but it still explodes, yeah. The bet we have is that we do this streaming operator where we can actually filter on the fly and then even avoid to materialize them in the memory of the computer, but you still have to go over them and ditch them. And containing that second thing of explosion and basically being able to hint at, well, I want to start leapfrogging in such a way or such other way to just avoid looking at some of the candidates and enumerate them in a specific order. I don't think we have a good solution for this, but leapfrog is cool because you can actually guide, you can select which atoms you start with, and so you could maybe avoid explosion this way, but I don't have a good answer.
Thanks.
Okay, and let's thank the speaker one more time.